Good evening, everyone. Welcome. Thank you for joining us for our Astronomy on Tap for the month of June. It is June. I'm Dr. Cameron Hummels. I will be your MC for this evening's event. Thank you for spending your Monday night with us, space enthusiasts. So a schedule for tonight, I'll have a couple of announcements and then we'll launch into our two talks. The first talk will be about probing distant galaxies by using gorging supermassive black holes by Dr. Britt Lundgren from University of North Carolina, Asheville. And then, so that'll be about a 15 or so minute talk followed by Q&A from all of you guys. And then the second talk will be Dr. Junhan Kim, who will be talking about, I forget the exact title, but studying the universe from the South Pole, our South Pole, the Earth's South Pole. He's been there a number of times doing astronomical research there, so he'll share both the science that's being done there as well as the experience going to the South Pole, which should be super sweet. And then, so the two talks, as I said, are about 15 minutes apiece, about 5 to 10 minutes of questions. That'll take us through the first hour. And then the second hour will be all interactive pub trivia on space-related themes and space-related questions. So this is an opportunity for you to prove your knowledge of astronomy. It's super fun. There's a web page or an app page. You don't have to log in or anything like that. You just go to it and the questions will pop up, but they'll also pop up on our screen. And when you type in your answers, we see how you're responding in real time, so we can get a feel for who's answering what and if everybody's doing really well or not. And there's a range of different levels of questions, you know, some really easy and some more difficult. So it's super fun. This is also traditionally, because it's Astronomy on Tap, it's held in a bar. So we encourage, if you're legally able to do so, to join us for a beer. I actually need to grab a beer from the fridge, but I'll do that in a moment. And yeah, what else? So next month is our 5th anniversary of Astronomy on Tap Los Angeles. We're gonna have something special, I'm sure. I'm trying to work out who our speakers are gonna be. So stay tuned for high-profile speakers. So far, I've invited 2 Nobel laureates. They haven't said yes, but they might. So we'll see. That could be pretty sweet. And next week, if you happen to be a Mandarin Chinese speaker, we are hosting Astronomy on Tap in Mandarin. This will be our second event like this. We had one 3 months ago and had 8,000 attendees in China, which was pretty sweet. So we're doing that again. It'll be next Monday. You can, if you're on YouTube or Facebook, you can see the events already announced. And the event will be entirely in Mandarin. So if you speak English and not Mandarin like me, it's probably not worth attending because you won't be able to understand very much. Anyway, okay, those are all my announcements for now. Britt, Junhan, Austin, you guys want to jump on here? Say hello. Welcome, team. Thanks for joining me tonight, especially Austin and Britt, who are connecting in from the East Coast, where it's quite late.
Happy to be here.
What's that?
Happy to be here.
Oh, awesome, awesome. Well, me too, me too. So are you guys consuming any beverages for the event? Ooh.
I went with Full Steam, which is in Durham, North Carolina. They make this rocket science.
I like it.
Which is very nice. It is an India Pale Ale from the beautiful South.
That's cool. I've heard that North Carolina has a huge number of good breweries, but I've never really partaken in any of them. I don't think they're widely distributed, at least not out this far west.
It's a big thing in Asheville, especially.
Yeah, I hear Asheville is the place to be.
It is.
I know a few people there, and it sounds like a pretty sweet gig.
It's not bad.
Nice. Junhan, what is that you had?
This is Mission Blonde, and can you see this? Yeah. My
Very nice. I like the sundogs behind you. I think that's a sundog. Isn't it a sundog, or is it just a
That's
halo?
right. And I took this picture. Yeah. So
Oh, cool. Is it the South Pole Telescope?
that is. So yeah, that's a 10-meter diameter. As you can see, a radio
Awesome.
telescope. Yeah. Which
Awesome.
I'll be talking about.
Awesome. Cool. And Austin, you're sticking with water for now?
Yep.
A healthy choice. It's wise. Hydration's important. All right. Well, I guess let's get started. Britt, you're gonna start us off, right?
Sure.
Cool. Okay, so Dr. Britt Lundgren is an associate professor of physics and astronomy at the University of North Carolina, Asheville, whose research involves using observations from the Sloan Digital Sky Survey and the Hubble Space Telescope, everybody knows the Hubble Space Telescope, to study how the gas in and around distant galaxies shapes their evolution over time. She is an upper Midwesterner at heart, but has warmed to the temperate climate of the Blue Ridge Mountains and regularly enjoys its trails, craft beer, bluegrass, and black bears. I didn't know there were black bears in North Carolina.
There
Wow.
are. Yes.
Do you regularly encounter them on hikes?
Yes. Yeah. And sometimes in my backyard
Whoa.
on occasion. So yeah, we had one walk directly across the quad during last year's graduation on campus also. Which was pretty
Yeah, there are some
hilarious.
black bears in the San Gabriels near just north of Los Angeles that people encounter. I've only encountered their scat on the trails. I have not encountered them themselves.
Probably for the best.
But yeah, scat, not as good as the real thing.
At night around campus, sometimes it's hard to distinguish if it's a dog or a bear. So you gotta be careful. Yeah.
Yeah.
That's wild. Cool. Okay. Well, you want to take it away, Britt?
Sure. Can you see it?
Yeah, it looks great.
Great. Okay. So thank you, Cameron, for the invitation. This is exciting. I've never given a talk in LA from my guest bedroom before, so this is really breaking the mold. But I'm really excited to be here. This should be a lot of fun. I'm just going to talk for like 15 minutes, tell you a little bit about a little known technique for finding and studying really distant galaxies that utilizes kind of counterintuitively supermassive black holes to illuminate those distant galaxies. So I'll tell you how that works in a second, but first I want to just quickly give a shout out to my current location in the beautiful Blue Ridge Mountains. Like Cameron said, I'm from the Chicago area originally, and I miss my snow, but it sure is a beautiful place to be. So these are almost the oldest mountains on Earth. I think they're second oldest. And they used to be as tall as the Alps, and they've been eroded over a few 100 million years. But they're really stunning. They're great for hiking if you like hiking in the shade, if you're a pasty person like me. In a grander view, here's where all of us are, right? In the Milky Way galaxy, about halfway out from the center, which is about 26,000 light years from the center of the galaxy. And of course, this isn't a real image. This is an artist's impression of what our galaxy looks like, because we don't have the technology to take a picture from this far away and get a nice bird's eye view. But we have plenty of scientific evidence to say that this is a pretty reasonable picture of the galaxy that we call home. Now, when I think about galaxies, I take an even bigger view. So this may not be how you're used to thinking about the Milky Way, but in fact, the part that we can see in terms of its stars is really just about 1/10 of its total size. Our Milky Way, just like most galaxies, is surrounded by a massive kind of spheroidal halo filled with dark matter, but also lots of gas. And we've known for a decade or two that there's actually tons and tons of stuff in that halo. There's approximately as much mass in the halo of our galaxy as there is locked up in the stars that we more commonly associate with the Milky Way and the disk. So this is kind of the context for what I study, which is also known as the circumgalactic medium. And if you looked at another cartoonish view of the Milky Way, you would notice in this kind of illustration that gas in the extended halo is not actually static. It's dynamic. There are lots of processes of accretion and outflows from winds blown by supernova, which are the events that mark the ends of the lives of massive stars. And also there's some outflows that can be caused by activity around the supermassive black hole that lives at the center of the galaxy. And if we could watch our galaxy for, millions and maybe even billions of years, you would be able to see how all these processes play out in full. Now, of course, over the span of a human lifetime, that's not possible. And we can't really easily turn back the clock and make a movie of what's happened in our own galaxy, but we can make beautiful and very realistic theoretical simulations, just like this one that I'm about to show you by our own host, Cameron, which comes from the FIRE simulation collaboration. And what I'm going to show is a formation of a galaxy kind of like our own, so a typical disky spiral galaxy. And what you're going to be seeing is how it grows over time through the accumulation of gas, which is drawn by gravity from the surrounding cosmic web. So if I play this forward in time, hopefully you have enough bandwidth to see this. If you focus towards the center, you can see the growth of this galaxy as it gains mass from mergers with other galaxies in its local environment, and also, fresh gas that's coming in from that cosmic web. So over time, you'll see some organization of that galaxy into a nice spiral disk, which is what you see after a few billion years at the end of this simulation. Now, if you were to watch this same simulation, but not paying attention to the density of the gas, but instead encoding the pixels of the video by the temperature of the gas, you would see something even more dynamic and perhaps kind of shocking. So here what you can see is what's going on with the really hot gas. And what it looks like are a bunch of big explosions happening in various locations in the halo of this galaxy, which seem to be spurred by the accretion of satellite galaxies and other inflowing kind of clumps of gas, right? So we think that this is a really realistic simulation of this kind of feedback mechanism that's caused by bursts of star formation that are soon followed by bursts of supernovae, which together can blow out lots of million-degree or even hotter Kelvin gas out into the halo. And depending on how massive the galaxy is, that gas may or may not fully escape out into intergalactic space. So these processes we now have really detailed predictions for, and we can understand them through the simulations, but still we'd like to see that they fit with what's going on in the real universe. Let me show you, before I move on to observations, just kind of another final cartoon that encapsulates all of these processes. So we think if you were to freeze frame one of Cameron's movies kind of in the middle, you might notice that gas has been accreted along what we call the major axis of the galaxy, which draws gas into the disk region. There is probably some outflowing gas caused by those supernovae, which tend to follow the path of least resistance, which causes winds to poke out of the disk of the galaxy perpendicularly. And so you have these outflows extending perpendicular to the disk, and some of them are recycled because they're drawn back because they're too low velocity, or the galaxy is too massive, and they come back and kind of rain down and recycle in the disk of the galaxy. But other winds may be able to fully escape and blow gas fully out of the halo into the surrounding medium. And so we think all of these processes at some point or another have happened in the lifetime of a massive galaxy. And so we don't think this is a ridiculous theory, right? We can look out at some nearby galaxies which are still in the process of rapidly forming stars, and we can see evidence that they too are blowing huge amounts of gas perpendicularly out of the disk of the galaxy. Like what's shown here is the M82, which is a local galaxy also better known as the cigar galaxy. And the disk of the galaxy is shown here kind of in blue light, where you see a lot of starlight. And then the red features trace out regions of active star formation, which also have this really characteristic biconical outflowing formation. And we think that this kind of geometry is probably really characteristic of galaxies that are still in an actively star-forming, star-bursting phase, which is more common in earlier times. So people like Cameron and me, who spend a lot of time thinking about gas around galaxies, don't do it just for the sake of thinking gas is cool or wanting to know precisely what's going on with the winds. There's actually a really big driving question that motivates this kind of study of the gas and dust that surrounds galaxies. And the question is, why is it that in the modern day universe, galaxies are forming fewer stars all the time? So on average, if you look at the average rate of stars being formed in the entire universe, just on average over time, you would see that today is a relative low, right? You'd have to go back in time 10 billion years to get to the point where the universe was most actively forming new stars. So something's been happening for about 10 billion years that seems to be shutting down star formation in galaxies. And of course, star formation is important because it's what helps to grow the visible portions of galaxies. And converting gas into stars also enriches the universe, produces heavier elements. And so we really would like to understand what's governing this formation of new stars, and why galaxies overall are forming fewer today than they have in the past. So we think that the gas is probably very close to the answer, right? You need gas to form stars, but it can't just be any gas. It has to be cold enough so that the clouds of gas can actually collapse into structures that are dense enough to ignite nuclear fusion and become what we refer to as stars, right? So anything that drives gas out of a galaxy or simply heats it might be sufficient to totally shut down the process of forming new stars in that galaxy. And so winds from supernovae and winds that are caused by active galactic nuclei or active supermassive black holes, we know should be able to produce those kinds of winds and also heat the gas. And so we'd like to know more about them. And doing so really requires studying where gas is around galaxies, what it's doing, what its physical conditions are, and how that changes over time. Now, that's easy enough in galaxies that are close by, but if we want to know what was happening at earlier times in cosmic history, we need to study galaxies that are farther away, galaxies whose light has taken billions of years to reach us and is therefore giving us a snapshot of how they looked in the distant past. Now, this is a challenge because gas is not very bright even when it's close to us. And when it's cold, it's virtually impossible to see. So how do we detect normal matter? I'm not talking about dark matter, but normal matter that happens to be dark, right? Turns out you know intuitively how to do this. You do this all the time in your normal life. You go out at night, the moon's out, and you can see things that are obscuring your view of the moon. So backlighting is one very, very simple way of doing this. Now, thanks to quantum mechanics and the physics of the universe, this backlighting can be super, super powerful depending on how it's done. So if you have a source of a continuous spectrum, so something like the sun, a star, or as we'll talk about soon, a quasar, backlighting a cloud of diffuse gas, some of that light, which would otherwise produce a continuous spectrum like a rainbow if you passed it through a prism, very specific wavelengths of that light will be absorbed by that cloud of gas and redirected. And so if you're looking from behind the cloud towards that continuous light source, you would see very specific wavelengths of light are missing, And those specific patterns of dark lines on the spectrum, what we call absorption lines, tell you precisely what that cloud is made out of. And for reasons I don't have time to get into right now, the shifting of that whole pattern of lines towards the red or longer wavelength end of the spectrum will also tell you exactly how far away that gas is if it's at a cosmological distance. So this is an extremely powerful tool. It allows us to basically take samples of clouds and distant galaxies and know what it's made out of and know its physical conditions without being anywhere near it. Now, the only trick is that if you want to do this for really distant galaxies and really distant clouds of gas, you need something sufficiently far away and sufficiently bright to serve as your backlight. So the universe, again, has been quite kind. There are these objects known as quasars, which have been discovered in the 60s, and we've been studying them for decades. And we now have good reason to believe these are actively accreting supermassive black holes at the centers of distant galaxies. What happens, we think maybe as a phase in any galaxy's normal life, is that gas can fall onto the center of the galaxy where there's a supermassive black hole. And that process of accretion of that matter onto the supermassive black hole heats up an accretion disk and produces an intense amount of light and energy. And in fact, the light that comes from this very small region around that supermassive black hole, which will have masses of millions of stars like our own sun, that small region around that black hole will be luminous enough to outshine all of the stars in that galaxy combined. So a galaxy that has a supermassive black hole in this quasar phase will be 100, maybe even 1,000 times brighter than it would have been otherwise, just by the light of its stars. So this means we can see them from much farther away in the universe than normal galaxies. And so they make excellent backlights for all of the other stuff that we want to see in the distant universe, but that's too dark and too far away. And so what I work on is taking spectra of distant quasars and looking for dips in the spectrum of their light, which indicate the presence of gas somewhere in between us and the quasar. And the pattern and its shift tell us what that gas is made out of and where it's located. And so we can basically sample the universe extremely precisely from an immense distance using this method. Now, the only downside is that these quasars are pretty rare. In fact, when I first started this work, there were only maybe 1,000 or 2,000 of them that had been identified to date. Which makes it really hard to study galaxies using this kind of backlighting method, using a lot of quasars as different skewers and probes of different parts of that gaseous halo to build up a picture. So instead, what we have to do is just find many, many more quasars and statistically study what they find when they probe, thousands or hundreds of thousands of galaxies as a large statistical sample. So I've spent a lot of time over the past now almost 20 years working with the Sloan Digital Sky Survey, a very large international group of astronomers that have been using this telescope located at Apache Point Observatory in New Mexico to map out in 3 dimensions the night sky, about a third of it, what's visible from that location. And in doing so, this has produced one of the first really big digital surveys of the sky, collecting spectra for 1 million nearby galaxies and 100,000 quasars. In the last decade, this has even scaled up more through upgrades to the spectrograph. And we now have a sample of about 500,000 quasars, each of which is like a core sample of the universe. So this is an enormously rich data set, which now poses its own challenges in terms of analysis, right? When you have 500,000 spectra, how do you even find all those patterns? So something I've been involved with again for some time is training computers to do it for us, to extract patterns that are pretty easily recognizable and catalog them, and thereby allow us to make a map in 3D of the locations of distant galaxies that are otherwise too faint for us to find. Now, this works pretty well, but frustratingly, there are some places where it still barfs. And so, so my research assistant, Austin Shank, who was formerly a student at UNC Asheville in computer science, has been helping me develop this project, which is being launched very soon on the citizen science platform Zooniverse. This project is called Invisible Galaxy Zoo. And if you're interested in doing a little bit of classification for us and joining in on the research, you could consider today kind of a soft launch. We haven't launched it formally yet, but you can find it at this link and test it out. And we would love to get your feedback and hear what you think of it. I just want to tell you one more thing before handing it back over to Cameron, which is that even if we can make giant atlases of where these markers of distant galaxies are located by finding the gas that's associated with them, it still doesn't tell us quite as much as we'd like to know if we really want to test those beautiful simulations and see if they're right. In fact, when you look at the images of quasars from the data that we use to find them in the first place, they look like this, not great. And that's because our telescope is located on the ground. It's not particularly large. It's 2.5 meters in diameter. And so things just look kind of fuzzy. Now, if you use a space telescope of the same diameter aperture, and look at that exact same quasar, you can see things much, much better. The lack of atmosphere really helps. The sensitivity of Hubble is exquisite, and you can see it's much better resolved. And in fact, there are a number of galaxies in this image, any number of which could have produced the absorption that we see along the line of sight. So I've been working for some time getting Hubble observations of interesting high value quasars that we've found doing this kind of mining of quasar spectra, and been working to build up samples that are large enough to tell us what the gas looks like in terms of its spatial distribution around galaxies in the very early universe. So we finally have a big enough sample, which is still not as large as we'd like. Something like 60 of these absorbers match to actual galaxies that we can identify in Hubble imaging. And this has allowed us to see that, in fact, when the universe was about half of its current age, we do see those same kind of outflows around star-forming disk-like galaxies, the same kind that we see in the Cigar galaxy in our local universe. This seems to be a pretty common feature of star-forming galaxies about 6 billion years ago. So this is really exciting. It's hard to build up big samples, but quasars are really key to the process. And that's all I'm going to say. I'll leave it open to questions, and also put up this web address again if you want to get involved with the team and the project. That would be fantastic. So thank you so much.
Awesome. Great job, Britt. Yeah, I will post that link in the chat for people so that they can click on it if they're too lazy like me to actually type it out and everything.
Great, thank you.
Excellent presentation. So yeah, we encourage viewers, if you're interested in asking questions, by all means do so. In the comment section, both on YouTube Live as well as Facebook Live. Yeah, so feel free to ask questions and we will try and address them. There is a question here from Andrew Reitemeyer. Can you see gas clouds nearby or behind the quasar by reflected light, as well as this kind of backlighting effect from the distant quasar? Or is it just absorbed, or is it also reflected?
So if I understand the question correctly, that actually is something I've entirely swept under the rug, which is that there is absorption close to the quasar itself, which can be really complicated to interpret. So there's both absorption and emission very close, due to that accretion disk going around the supermassive black hole, and that can also drive a very strong wind that can actually make it look like we're looking at a galaxy that's in between us and the quasar, but it can actually be relativistic gas coming out of that region very close to the quasar, just at a really high velocity along our line of sight. So things do get complicated with both, the emission in that region and also the absorption in that region. And my main efforts have focused on kind of ignoring that. Since my first paper in grad school, there's really interesting variability that happens on very short timescales with the emission and the absorption very close to quasars. And that's a whole interesting area of research as well. But yeah, it gets tricky.
Yeah, super tricky. That was a super cool result. So it looked like from the last plot that you showed that the bulk of the, if you want to show it again, the bulk of the matches were from kind of like the 50+ degree range, like you're seeing it at this intermediate angle, as opposed to, like, if it were 90 degree, it would be straight up out of the poles of this galaxy, and if it were 0 degrees, it would be along the disk axis. But this, it looked like your main thing is showing kind of at this opening angle of 45 degrees to 60 degrees or so.
Yeah, so I also brushed a lot of this under the rug, but thanks for noticing. That is true. I tried to make the cartoon look like the distribution in the plot. There actually is more detection along the edge of these cones, we think, and that agrees with simulations as well. And the reason for that is the gas that's traced here is a particular kind of gas, which is kind of medium temperature. So it's singly ionized magnesium, which traces gas enriched by stars very well. But it's not the hottest kind of gas you can trace. And so I think in regions of the outflow that may have gas, but at higher temperatures, that won't be traced by the specific kind of tracer that we were looking at in this study. And I think that the cones are also less dense in the center as well. But I don't know, Cameron, maybe you actually know more about the simulation.
I was having a meeting with a student today to look at this in the fire simulations, like the movie that you showed. By the way, I did not pay her to put that movie in here. She chose that movie. It's a cool movie. But no, I was meeting with a student today who's trying to look at this in the fire simulations to see if there's a preferential angle. This is, I always like to have models around here to describe the thing that I'm talking about. If this is the disk of the galaxy and these are the polar angles, if there's a preferred angle at which you see this singly ionized magnesium or other different ions that are indicative of outflows in the simulations that can help to, basically doing the simulated version of what you did in this observational work. So
I look forward to the results.
More to follow in the next couple of months. Hopefully, we'll see.
Great.
Let's see. Are there other questions? There are other questions. How about this one? The Nerdy Walker asks, how different is the temperature of the gas in the circumgalactic medium in distant galaxies compared to ones that are closer by, that are nearer to us?
That's a really good question. So it depends. It depends on what kind of galaxy you're talking about. So we know that the temperature of the gas around galaxies in the circumgalactic medium depends a lot on the total mass of the galaxy. So if you look at a really, really massive galaxy, those halos tend to be really hot. So you don't see a lot of the intermediate temperature tracers like I tend to focus on. You see higher, like triply ionized carbon or 5 times ionized oxygen. Those tend to be better tracers of the hot gas in more massive galaxies. Now you tend to find more massive galaxies at greater distances because you need a lot of volume to find them in the first place. But over time, of course, more massive galaxies become more common at later times. So it's a little bit complicated, but I think instead of thinking about how things looked further in the past, I think we tend to, when we're thinking about the CGM, think more about the type of galaxy that you're seeing. But something that does change at earlier times, the tendency of galaxies to have disks is something that we don't see at very early times. It takes time to form those disks, and then they become, I think, less common at later times as well. So there is a time, if we looked further back, we might not see these really well organized outflows. Because if you don't have a disk, you don't really have the structure to
have that angle. Exactly. I would agree. Looking at the simulations, I would totally agree with that statement that things are a mess when you look farther and farther away, indicating that it's earlier and earlier in the universe when that galaxy existed in that state that we're seeing it in, and things are not as well defined as having like a disky galaxy. It's just like a blob of craziness. So
yes. Well, JWST will.
Yeah, hopefully
that for sure.
More information. And that's cool that you have this Galaxy Zoo project associated with everything. Very cool.
Yeah, try it out. I don't know. People usually like to look at images, but try out looking at spectra. See if you get addicted to them too. But
absolutely. One last question from Stephen Schreier. What is the most distant quasar you've observed, and how many solar masses might be the various quasars? Also, thank you. Excellent presentation from beautiful Asheville.
Oh, thank you. So I think I saw Zhaoyi Fan tweeting about a new most distant quasar very recently, but I would have to Google it.
No, but I think the question was how far, what's the most distant quasar that you personally have?
Oh.
Or maybe it's you as like all of astronomers, us, what's the most distant? Yeah, that is a good question. I figure the highest redshift galaxies, or the highest redshift quasars that we've observed are 10, 11?
I was going to say 11.
It's about to be.
I'm not sure I want to Google it. Do I get to Google it later? Phone a friend?
Oh yeah, that's okay. Yeah, sure. I don't memorize these off the top of, have them on the top of my head.
It's a good question, though. I mean, to put that in context too, we typically see quasars in the distant universe because they were a much more common phase of galaxies at earlier times. And there are a number of models that think that can be explained through mergers, for instance. Anything that's kind of allowing gas to funnel into the center of a galaxy could activate that black hole. And we think that was just a more common thing earlier in the universe, which is supported by the fact we tend to see them very far away.
Indeed. Indeed. And it's a big problem because we don't know how to build up these supermassive black holes to as massive as they appear to be as early as we see them in the universe. Like there's just not enough time after the birth of the universe to build these things up according to the physical mechanisms that we now understand. So it's like people are actively trying to figure out, how do you build a supermassive black hole up super, super fast, a few 100 million years after the birth of the universe, so that they're at the mass that we can actually see them as these quasars when we look across these vast distances. So yeah, super exciting stuff. Super exciting stuff. Cool. Okay. Let's transition to our next speaker for this, Jun Han. Hello, sir.
Hello.
Oh, and I ended up getting a beer. Two Hearted Ale. I'm a big fan of Two Hearted Ale from Bell's in Kalamazoo.
That's a good one. Also.
Good. Yeah. So you're from Wisconsin, is that right, Britt?
The very top of Illinois, Rockford.
Oh, sorry, I didn't mean to lie.
It's close. It's fine.
But yeah, so I suppose Kalamazoo isn't too far away. I guess it's like 6 or 7 hours drive. It's a ways.
Depends on how you get there. Yeah. Go up and around, or anyway, I'm gonna bow out.
Yeah, no worries. Welcome, Jun Han. Let me give my introduction for you. So Dr. Junhan Kim is a postdoctoral fellow in the Observational Cosmology Group here at Caltech. His research program spans various topics, including galaxies, galaxy clusters, and supermassive black holes. And in addition, his work involves developing new radio telescope instruments. He's traveled to the South Pole 5 times to work at the South Pole Telescope located at Amundsen Scott South Pole Station in Antarctica. We overlapped when I was a postdoc at Arizona and you were a graduate student. And yes, that's awesome that you've gotten to go to, have you gone elsewhere on the Antarctic continent aside from just Amundsen Scott, or you were just always going to Amundsen Scott?
Yeah, I always go there, and we fly through the McMurdo station around the coast. I will show you some pictures, and yeah. That's cool. I would love to.
Yeah. That's cool. Okay. All right. I will let you take it away, sir.
Okay, let me share my screen. Can you see my screen?
I can see your screen, and it looks great. It looks great.
All right. So, okay. Hello, everyone. I'm Junhan. Thank you all for joining us tonight. And as Cameron mentioned, I'm a postdoc here at Caltech. And as a experimental astrophysicist and radio astronomer, some of my projects involve instrumentation development, and I often visit remote sites in the world. And the South Pole was among them, primarily for my thesis work before coming to Caltech. And many cool sciences are happening at this unique, exotic place in Antarctica, including astrophysics projects like studying the light from the Big Bang, even the black holes. So in this talk, I will briefly introduce the project I've been involved for many years and tell you why astrophysicists go to the South Pole, how they get there, and what's happening there. So if you have any questions, please leave those on the chat and I'll answer them after the talk. Here we see beautiful images of the galaxies and the universe. And as Britt already mentioned in the previous talk, there are objects called supermassive black holes at the centers of most of the galaxies. And one of the most popular supermassive black holes to the public must be this one, I believe. And the supermassive black hole at the center of the galaxy M87 in the constellation Virgo. And many of you may remember this image from the news in April 2019. And this is the first ever picture of the black hole captured by the Event Horizon Telescope EHT collaboration. And I remember my Caltech colleague, Katie Bowman, gave a virtual lecture series in this Caltech Astro channel last November, so I won't go into too much detail. And it would have been great if we could directly observe all the supermassive black holes in the universe and solve mysteries, but that's impossible, right? And there are several reasons, and one of them is simply because the apparent size of the black hole is too tiny in the sky. And the size of the emission, let's see if you can see my cursor here. Yeah, this is the size of the emission, that bright narrow ring feature, which comes from the matter falling into the black hole, is proportional to its mass. So for instance, this black hole, its mass is approximately 6 billion solar mass, and the diameter of the ring is about 60 billion miles across, I believe. And the apparent size of the black hole gets bigger as it becomes more massive, but it becomes smaller and smaller in the sky as it gets further away from us. And since this particular black hole is 55 million light years away, the diameter of this ring-like emission is about 40 microarc second. So microarc second. So what's the scale we're talking about here? If we want to understand the observation, we need to talk about the scale of astronomical sources. And astronomers often use the unit of angle or angular measurement to show the size of the object or the distance between the object in the sky. So let's hold up your finger at arm's length, point toward the sky, and the width of your finger approximately corresponds to about 1 degree of all 360 degrees around. And the moon is about half a degree across. And apparently the black hole at the center of M87 galaxy we've seen is significantly smaller than that. So let's understand how small micro arc second is. So within a degree, there are 60 arc minutes, which means that 1 arc minute is 1/60th of a degree. Then there are 60 arc seconds within 1 arc minute. Then we have 1,000 milliarc seconds within 1 arc second and 1,000 micro arc seconds within 1 milliarc second. So the size of the black hole we talked about is about 40 micro arc second across, and that's 90 millionth of a degree, or the size of your finger on the sky. So observing this size of the object is, something like similar to observing a softball on the moon, or a grapefruit, or a donut. There are lots of analogies here, but yes, we're talking about a donut. So we need a telescope that can resolve a donut on the moon. So we need a large telescope, or a telescope with high angular resolution. The higher the resolution of the telescope, the more details we can see from the sky. The resolution of a telescope is dictated by 2 factors: wavelength you're observing and the diameter, or the size of the telescope. And the resolution is inversely proportional to the size of the telescope or a mirror. Of course, the larger the telescope is, the smaller the size you can resolve in the sky, and it's proportional to the wavelength. The shorter the wavelength is, the higher the angular resolution it gets. And these are famous telescopes you might have heard of: the Hubble Space Telescope and the Keck telescopes on top of Mauna Kea, Hawaii. They observe optical and infrared light, and their angular resolution could reach few hundreds of arc seconds. No, it's good, and astronomers use it for research, but it's not enough for our purpose. They are still a few hundred times worse than what we need. So fortunately, astronomers developed a technique to make telescope bigger. The technical development on the very long baseline interferometry, VLBI we call it, in millimeter wavelength in radio, enables us to reach that high angular resolution with telescopes worldwide. Like here, we observe astronomical sources. In this slide, we're observing a black hole using the telescopes separated apart simultaneously and timestamp the data and correlate the signals later. So basically, we synthesize a telescope out of many telescopes distributed all over the surface of the Earth. So what matters in interferometry, also in very long baseline interferometry, VLBI, is this baseline, the separation between 2 telescopes that sets the angular resolution we can get, because it basically sets the size of the virtual telescope we will have. So in this way, by combining the radio telescopes around the world, the Event Horizon Telescope Array acts as a virtual Earth-sized telescope. Hawaii, Arizona, Mexico, Chile, Greenland, and the South Pole. In fact, this is a configuration from 2018 observation. And for this year's observation that happened about 2 months ago, we added telescopes in Arizona and French Alps to this array. And also the Owens Valley Radio Observatory near Bishop, California, operated by Caltech, is scheduled to join this array soon. So that's a summary of the project, and hopefully you now understand why we need an Earth-sized array of radio telescopes. And here you can see that this telescope, marked as SPT, South Pole Telescope, on this white continent that maximizes the separation between the other telescopes. And that's why I had to develop an instrument and go to the South Pole. Someone has to assemble a telescope and taking the observation to get the data. Yeah, so I will move on to the South Pole part. But before we move on to the South Pole part, there's a mid-roll advertising here. This documentary, Black Holes, The Edge of All We Know, by Peter Gallison at Harvard and colleagues, is on Netflix now. And this film features this international effort to make the first direct observation of the black hole I just described. So make sure you check it out if you're interested. So as you've seen, the Event Horizon Telescope array consists of many radio telescopes around the world. And the telescopes need to be equipped with an instrument that can perform very long baseline interferometry observation. However, the South Pole Telescope, SPT, did not have the detectors we could use for the EHT because it was originally designed to do completely different science. It is the telescope used to look for the cosmic microwave background radiation, which is a leftover radiation from the Big Bang. In fact, the cosmic microwave background, CMB, is one of those primary astrophysics science at the South Pole, along with the neutrino telescope called IceCube. And my project was somewhat tiny there. So I really encourage Cameron to recruit someone from the observational cosmology group to talk about that in the future events. Anyway, so yeah, South Pole Telescope is really important in the EHT array because it's far south and almost doubles the size of the virtual global array, especially when we're looking at observing the black hole at the center of our own Milky Way galaxy. And I also want to emphasize that making the array bigger is not enough. We need a sensitive array. So to detect this tiny signal from the black hole, we have to go to this highest, driest place on Earth. And that's because the radio signal is absorbed by the water vapor in the atmosphere. The atmosphere is not your friend when it comes to astronomical observation. And that's the reason why most of the world-class observatories are located on top of the mountain, like in Arizona, Hawaii, Chilean desert, sometimes above the atmosphere. So for this very telescope, we had to design and develop a specialized receiver. And this has been a many-year project starting in 2013. And this shiny golden metal block here is the receiver, basically a single pixel camera that can coherently receive the signal from the astronomical sources. And I don't remember when this picture on the right side was taken, but apparently I was a lot younger, many years ago, probably when Cameron and I overlapped in Arizona.
Yeah, this looks familiar. I mean, I wasn't there at the lab, but this looks like what I mean, you haven't, it's not like you're an aged, decrepit old man or anything. You're still very youthful, but this looks quite young.
I'm glad to hear that, but I'm old. Anyway, so yeah, that's lab back in Arizona, Tucson, Arizona. Then we went to the South Pole, Antarctica. And as Cameron mentioned, I've spent 5 austral summer seasons at the South Pole for this work. And yeah, it's austral summer season. So the season is opposite in the southern hemisphere. It's a long way down to the South Pole, as you could imagine. So first we fly to Christchurch, New Zealand on commercial flights. We then fly to McMurdo Station around the coast of Antarctica on this LC-130, a ski-equipped military cargo plane, and to the South Pole from there. And this is the inner view of the plane And as you can see, it's full of cargo, and basically people are a cargo. We are a cargo. So, and then finally, depending on the weather, because weather has to be good for the flight to take off and land on the ice, we arrive at the South Pole after a few days or even weeks since we left home. So another view of the plane. No, it doesn't look very convenient. No in-flight service, no in-flight entertainment with a screen, just a water and earplugs. And there's a restroom though, behind this curtain. And if you are lucky around the McMurdo station, around the Antarctic coast, you will get to meet these folks. Apparently there's no living creature at the South Pole except humans. And I once, there's a funny story. I once saw the reason, the flights are sometimes delayed, often delayed. And I once saw the reason for the flight delay was penguin herding across the runway. And I'm not joking here. So that happens. And the South Pole. We arrive here, Minson Scott South Pole Station, operated by National Science Foundation. And the geographic South Pole is about a minute walk from the station. And there is a lab or a building called Dark Sector Lab, about a mile away from the station. It's called Dark Sector Lab because we need an absence of electromagnetic pollution that would otherwise interfere with our experiment, because we observe at millimeter and radio wavelength, and we have all the electric circuits operating there. So on the left side is the South Pole Telescope I just talked about, 10-meter diameter dish. And on the right side, inside this metal shield, there's an experiment called BICEP and Keck, and that many of the Caltech observational and cosmology group colleagues are involved in. Then we start the work. The work begins. We assemble the receiver and even climb up to the telescope roof under this cold and harsh Antarctic environment. It's summer though, and this is how we do science. And yeah, that's the receiver I just talked about, the single pixel camera, and we three of us were sitting on the roof of the telescope. And on the right side is very specialized hardware. So we need some hardware such as a $250,000 atomic clock that can precisely timestamp the data, and the fast data recording system. And after many years of global effort, including multiple trips to remote sites, not only the South Pole, and extensive testing of the telescope system everywhere, we knew all the telescopes were working fine, and we were ready to do the observation and take the data. This is a time lapse of myself and our friend working on the roof. I think that's myself there. And it's interesting because sun never sets during the summer, and sun only rises and sets once every year at the South Pole. And the South Pole Station is only open during the austral summer seasons, and we all have to leave the pole by mid-February, and the austral winter begins. And we rely on people called winter overs who stay there for 9, 10, 11 months, who runs the experiment during the winter. It just doesn't sound easy, and we could do science with the help of all these people. So yeah, that's my story of why and how we explore the universe from the South Pole. And what I wanted to tell you was, often when we think of astronomy research, it's sometimes easy to think there are scientists working with computers, analyzing the data in the office, but there are species like myself. So I hope you enjoy it, and let me answer the questions and finish my drink. Thank you.
Great work, Junhan. That was excellent. Thank you very much. Awesome. Yeah, we encourage people to ask questions, audience members to ask questions in the Facebook Live and the YouTube Live comments. We've already got some here. Let's see. Does the atmosphere disrupt the seeing of radio telescopes at all, in the same way that the atmosphere affects? So for those of you who don't know, seeing basically means like when you look up in the sky and you see a star and it's twinkling because its apparent position is shifting around as the light traverses the atmosphere and refracts off the different parcels of gas in the atmosphere. Do you have a similar effect for the radio and radio telescopes, or is it turbulence, or do you just not have to worry about that at longer wavelengths?
Well, yeah, in longer wavelengths, we will, the effect is smaller. It's not very effective in longer wavelengths, but the wavelength we're observing in millimeter wavelength, the wavelength is about a millimeter, 1.3 millimeter. Yes, it's tiny. And the atmosphere matters a lot. As I described, mostly due to the water vapor in the atmosphere, that matters a lot. And that's why we go to these high sites. And South Pole is often, always, there are some bad weathers, but still the bad weather at the South Pole is still better than the other sites in the world. Yeah.
Oh, in terms of the turbulence and in terms of the atmospheric effects.
That's right. Mm-hmm.
I mean, the weather at the South Pole is arguably worse than other places, the bad weather in other places on the globe, when you're worried about like freezing to death or snowstorms. But in terms of the atmospheric like turbulence, it's much better than elsewhere, is what you're saying.
Not always, but often, yes. Mm-hmm.
Yeah, that makes sense. I've heard that at Dome C, which is
that's right. Mm-hmm.
One of these sites on the Antarctic continent, the average seeing, the average blurriness to your image is like 0.05 or 0.1 arc seconds or something. That's just like outrageous. Mauna Kea is normally like 0.4, 0.3 arc seconds. So it's like substantially better than what you can see. And Mauna Kea is considered one of the like premier observing locations in the world. And yet,
I don't know. It was snowing the one time I had time on Keck. So I'm going to have to disagree.
Well, I was an optical astronomer a long time ago, but yeah, I really don't have a sense of seeing nowadays. Yeah.
Let's see. Other questions. Are there plans, Piper Tripp asks, are there plans to put a large radio array at a high northern latitude to get approximate symmetry from your southern location with a northern location as well?
Sure, yes. As you see, there's the Greenland telescope. And,
right, that's you mentioned that.
Yeah, and as I mentioned, I didn't have that in my slide, but one of the telescopes just added this year was northern millimeter. I don't remember the full name, but it's called NOIMA.
Where is it located?
It's in the French Alps.
Oh, okay.
Yeah.
Okay. Cool.
But sure, yeah, more telescope, the better.
More telescope, the better.
That's every astronomer's dream, right?
Here's actually another question from Piper Tripp, but it's a well-posed one. Are satellite constellations, like Starlink or Jeff Bezos is launching a series of these satellites, these mega constellations, are those going to pose significant challenges to radio arrays in the same way that they're causing problems for visible wavelength astronomers? When we have our visible telescopes and we look up and we see a Starlink satellite go overhead, it leaves a star trail. Is this going to be a problem in the radio as well?
I don't think I have a great answer to that, but it matters because I don't remember the number, but they're they have to transfer the data in uplink and downlink, and their frequency is about what, a few tens of gigahertz, and they certainly overlap with some band, radio band. So I'm sure there's an effect.
Sure,
but
yeah. Well, and RFI as well. I imagine
that's right.
Radio frequency interference that it's, not only at which wavelength it's broadcasting, but just having a radio source in the sky that might pass through your beam, I could imagine causing problems too.
Yeah, and certainly there were some discussions going on. I haven't paid much attention to that, but
yeah. Okay. A couple more questions. Michael Cho asks, I hope this question fits the scope of this talk, but Dr. Junhan, can you talk about what it means to be an experimental astrophysicist? Since so much of what we're doing, certainly me as typing on my computer, I'm not really experimenting in the same way that you are.
Lots of adventure, I would say. No, I never knew I would visit South Pole until I entered the grad school. And yeah, a lot of we spend a lot of time in the lab and those observatories. And I used to often visit Mount Graham in Arizona. Have you ever visited there, Cameron?
Mount Graham is the one to the east, right?
That's right, east. Yeah, with LBT and Vatican Observatory. And
yeah, so no, I didn't ever go to Graham. There was a bicycle race that happened every year going up that climb, and I always wanted to enter, but I never did.
Yeah, so I would say it's tough, but I've been enjoying this a lot, and and sometimes, for example, soldering. I sometimes need this mindless job. So yeah, I've been enjoying this a lot. Yeah.
That's awesome. Let's see. How many staff members are on site during the austral winter? So from here, like you said, you were there from like November, December to February or so during the austral summer. And then there were these people who remain on through the dark, cold season. How many people stay on at Amundsen Scott Base? Or how many people stay on for the South Pole Telescope specifically, I guess?
So as far as I remember, at the South Pole Station, there are 40 to 50 people during the winter. And we normally have two people, two scientists for the South Pole Telescope operation during the winter. And they usually help with their nominal CMB observation, cosmic microwave background observation. But when this Event Horizon Telescope observation happens, they help installing those receivers and get the data and make sure everything is working. The telescope doesn't catch fire. Yeah.
Right. Yeah, I many years ago, before going to graduate school, I applied to work on the neutrino instrument to do a winter over on IceCube. Although at that time it was called Amanda. It was before it was.
That's right. Yeah.
IceCube, and they didn't accept me because I just had a bachelor's degree, and they're like, "Who's this chump? We don't need this guy." But I think it'd be such a cool experience to just. I mean, that was pun not intended. To hang out in the cold for 8 months, but
well, yeah, I'm not surprised that you apply for it, but I don't think I can do that.
No? No. What about you, Britt? Would you do it? Would you go to the South Pole for 8 months and hang out?
Well, in a second, I would love to. I mean, that's what all the astronauts are doing these days. I always wanted to be an astronaut. We've been through a pandemic. We can
deal with isolation.
Exactly.
Yeah. And you get some beautiful skies.
Auroras and yeah.
Cool. Well, that's cool. The YouTube or the Netflix link that you provided about this documentary, I'll have to check that out. I wasn't aware of that. And your book.
Oh,
you have a book, don't you?
Oh, you're talking about my book. Oh.
Don't you have a book?
I have it, but I didn't want
Look
to
at it.
You don't want to talk about your
advertising.
book? I thought you'd want to promote it. It's cool.
Well, it's been a while, and
Oh.
yeah, let me see.
Yeah, show people your book. He wrote a book, everybody. He wrote a book.
Okay, so
Uh-oh.
Oh.
I can barely
Yeah,
see
this
it.
is a
Okay,
book.
there.
Apparently, it's written in Korean. So
So it's not translated to English. It's only in Korean.
not yet. Well,
Okay.
no, yeah, but it's been a while, and yeah, I wrote this book with my friend who is now a postdoc here at Observational Cosmology Group, who used to be a physics graduate student at Stanford, Jae-hwan, and yeah, this is the title. If we literally translate this title, that's exploring the exploring the universe from the South Pole. So that's how I got this title. Anyway, well, okay, thank you.
That's cool. Well, thank you. Thank you for your presentation, Junhan. Okay, so I know there are still questions, but we're running a little bit behind, and I want to make sure we have enough time for trivia, because I know some people. So I've had people come in and they're like, "Get past these stupid talks. We want the trivia, people. Keep it moving with the trivia. When's the trivia?" So we'll start with the trivia here. I actually just finished the trivia, so hopefully it's actually complete here. So I will share my screen.
While you're doing that, I think we should have a correction about the most distant quasar. We were speculating redshift 11 earlier.
Oh yeah, what is it?
7.62, which really is not that different from 11 in terms of look back time, but it's important to say. Yeah, so 13 billion years is how long the light has been traveling from that most distant discovered quasar. And that was published earlier this year.
Oh, okay. So it's only galaxies that are at substantially higher redshifts. So the highest quasar is 7.62, but the highest galaxy is like 11 or 10 or something.
Yes. Yeah, I was also thinking of the most distant galaxy.
Well,
so we stand corrected.
Thank you for correcting us, not, spilling out fake news to the world. I appreciate this. This is good. Okay. So everyone, Astronomy on Tap has this pub trivia that you are welcome to participate in. If you follow the instructions at the top of the screen and go to menti.com and then type in this code, it will bring up, here's already the first question. It will bring up these questions, and you can then on your phone or on another web browser, you can type in your responses and they will pop up here. So, please don't cheat. I mean, you can cheat. I can't be there and be looking over your shoulder and say, as you have literally all of mankind's knowledge at your fingertips with the internet. Well, geez, people are really, really hitting it hard here already. So the first question is, last week, NASA made, huge announcement that there were these two new major missions that were going to go to the moon, or not to the moon, that we're going to go somewhere in the solar, fake news. We're going to go somewhere in the solar system in the next decade or so. What is that destination? And it looks like people are honing in on an answer of our good friend and kind of sister planet, Venus. Oh, a Mars naysayer throws the gauntlet down. Kaboom. And the answer is indeed Venus. Let's see, move to this. Here's a really nice image. I've got these zoom images. Really nice image of Venus. I'm not sure, presumably this is in the infrared to be able to pierce through the very thick, opaque atmosphere that surrounds Venus. But as people described, the two missions, or people submitted, the two missions are called Da Vinci Plus. It's plus because they had previously submitted Da Vinci and it got turned down. So they added more to it and then redubbed it Da Vinci Plus, and Veritas. And there's this really nice little movie that NASA put together that we can watch here. I think you guys should be able to watch this here. Ooh, can you hear that, guys? Okay, sweet. Pretty sweet. It's pretty cool. I mean, it's like they got a movie producer to do this. It's like Michael Bay. He needs more explosions. But yeah, here, let's just talk for a second. I had no idea that these were, I feel like it was pretty big news. Pretty big news when this result came out this week. I didn't know that these were coming up. And then it was like, we've been in Mars fever for the last, 10 years. And then all of a sudden Venus is all the rage. So it's pretty exciting. Yeah, Da Vinci Plus is going to float down onto the surface and have a lander. It probably won't survive very long because the pressures and the temperatures on the surface are super, super high. But it'll actively be taking samples of the atmosphere as it floats down. And then Veritas is an orbiter that's taking images of the surface. So it's pretty cool. It's pretty exciting. Were you guys able to hear it okay? Or was it muted?
I'm hearing. Yeah, that video looked grand.
Yeah, looks pretty sweet.
Yeah.
Okay, so let's go to our next question. Got to figure out how to get back to this. Can you guys see this okay again?
Yep.
Okay, sweet. All right. There's always a Star Wars question, but this one is a little topical, at least for me. In Star Wars, Mustafar is the volcano planet where Anakin Skywalker battles Obi-Wan. What is its equivalent in our own solar system? Oh, people are already fresh out the gate with Io. Mercury, nice. Any other volcanic active? Oh, the Earth, true that. That's cool. I mean, you don't have to watch Star Wars. I enjoy it. I mean, it's pretty simplistic in many ways. Like one of the things that all the planets are just like a single biome, which is not like many of the other planets that we've discovered in, well, I guess Venus is kind of like a single hot place, but maybe we'll learn more about it in the next 10 years. I don't know. Saturn, Mars, Earth, Mercury, Io. Okay. What do you guys think? Britt, Junhan?
I went with Io.
Yeah. Junhan?
Io, maybe. Sorry, I had to go and grab another beer.
That's okay. By all means. Yes, the answer is indeed Io. This is not Io. This is, maybe I'm going to get sued by Star Wars here by showing this battle. This is a rendering from the film. This is the volcano planet of Mustafar. This is again artist rendition of Mustafar, not Io. So Io is a moon orbiting around Jupiter. Here's an actual image of Io, highlighting some of the structures. I really like that there's a structure called Thor. That's pretty sweet. And yeah, it's a moon that's super close to Jupiter, and because it's so close, it gets trapped in the gravitational field of. I mean, all the moons orbiting around Jupiter are in the gravitational field of Jupiter, but it's so close that it's like stretching and warping Io when it makes its orbit, because it's an elliptical and eccentric orbit. So it's going from regions of low gravitational force to high gravitational force, and so that causes it to kind of warp in the same way that as the Earth orbits around the sun, and the moon orbits around the Earth, it warps our gravitational field, so we get tides. And the tides are essentially just like water bulges that are orbiting around, rotating around the Earth. Well, those same bulges on Io, instead of being, on the Earth, the tidal bulges are like 15 meters in the highest point, 50 feet. But on Io, it's like 300 feet. And it's not made of fluid. It's actually like stretching and pulling the planet, which is causing all this active volcanism and volcanoes, which I think is pretty interesting. So yeah, tons of volcanoes on Io. I don't know if this is actually a real image or not. I'd like to think that it is, but I didn't double check this. But nominally, you have these volcanoes that are blasting a bunch of junk off the surface. Yeah. Oh yeah. And so the thing that I wanted to mention is, because why not, is that tomorrow I go to Iceland and I'm going to try, and there's an active volcano that's erupting there, and I'm going to try and collect lava from the volcano and put it in this full of water. And I mean, I'll be safe. I'll be safe with my protective gear. But yeah, I'm pretty.
Are you going to bring it back?
Yeah, I'm going to bring it back. I'll if I succeed and if I'm alive, I will bring it back and I will showcase it at our next Astronomy on Tap event. So that's the plan. Anyway, all right, let's keep rolling with this quiz. What is the elevation of the South Pole? We have a few different options here. This was mentioned during Junhan's presentation. So yeah, our options, I guess it only shows the ones that people have chosen. We're sea level, 1,000 feet above sea level, 4,000 feet above sea level, or 10,000 feet above sea level. And it seems like the winners so far are 4,000 and 10,000 feet above sea level. Again, you can look these up, but I encourage you not to, because it's not like you're going to win a prize. Your prize is knowledge. All of our prizes are knowledge. So just give it your best guess. And, 1,000 pulling up out of the dark horse candidate here. Well, I'm not going to ask you, Junhan, because you know the answer because you've been there. Mm-hmm. But yeah, naively, if I hadn't listened to your talk, I don't think I'd know the answer. I would just assume like 1,000 or 4,000 feet. I wouldn't assume sea level, because if it were sea level, you'd be in the water, right? You'd be in the ice. But yeah, the answer is indeed about 10,000, 9,300 feet. So, like 3,000 meters. I like your penguin suit. So were you a participant? Why do you have a number? You have like a bib.
So yes, that's when we had, South Pole is South Pole. And if you run around the South Pole, you basically race around the world. So there's a race called the Race Around the World every Christmas morning. And yeah, people often come up with some costumes, and I had my penguin costume there, and that's why I have those numbers on. And yeah,
that's awesome. What's the distance of the race?
About 2-3 miles.
Oh, okay.
I remember. Yeah, it's not very long, not very short, but yeah.
Yeah, I ended up. I looked a little into this, and I found that there was some like professional athlete who went down there intentionally, like he was just like, I'm going to hang out at the South Pole, and then he was going to set the like record for racing around the world. He looks pretty
well, actually, yeah, there's really
awesome.
a full marathon happening there, really.
Oh, really?
Yes.
Oh. I like the frost on his whiskers. At least it looks like frost. Maybe he has a white mustache though. So wait, so there's a full marathon that just runs around the pole?
Yeah, and I've never tried it, but because I can't.
It sounds rough, especially at 10,000 feet. Like even at temperate climates, running a marathon at 10,000 feet is no joke.
Right, but yeah, I don't remember the records, but yeah, people just finish in what 3-4 hours, and which is just
That's cool.
I don't get it.
Britt, you're a runner, right? Would you go do this? You want to participate in this marathon?
Yeah, sure. I mean, I'm a mid-distance runner. I'm currently in a boot.
Oh no! Wait, why?
Yeah, so I won't be doing that anytime soon. But
what happened?
It's unclear. It might have been running. It might have been working from home barefoot for too long. It's unclear. Something lame. What?
Like, is it a stress fracture or overuse or something?
Yeah.
Oh, bummer.
I know. Well, it might be. I don't know. I'm getting more scans tomorrow. But anyway, normally, yes, I would say yes. I would love to run this race.
Yeah.
It sounds hardcore.
You were a collegiate runner, weren't you?
I was.
That's awesome.
Yeah. D3, you know.
No, but still, that's good. Wow.
Same team as Edwin Hubble, though.
The same team as Edwin Hubble? University of Chicago.
Yes.
Nice.
That would have been a good trivia question. There you go.
Yeah.
Oh, next time.
Next time. Okay. Oh, speaking of Edwin Hubble, the Hubble Space Telescope launched on April 24th of what year? What do you think, people? How long has HST been around? Well, 1986, 1990. No looking it up. I'm looking over your shoulder as you type in Hubble Space Telescope year. Well, in general, people are getting all in agreement about roughly when. It's not like anybody submitted 2015. At some point, that's fair. That's a realistic response. Indeed. It's funny, you know, just as the James Webb Space Telescope has had a lineup, and we've been predicting that James Webb has been, you know, it was going to launch in 2012, and then it was going to launch in 2015, and it's Hubble had the same sort of business. So yes, the answer indeed is 1990.
Yeah.
Beautiful Hubble here, still going strong. I don't know. What do you think? I figure we aren't servicing it anymore, but it's some of the detectors are degrading and the gyros are going bad, but I figure it's got at least a few more years. Hopefully for you.
I hope so.
Yeah. But yeah, just like this is a nice comic taken from XKCD, I think, that shows the planned launch date at various points in the past. So the planned launch date is the top curve, the shallower curve. And you can see that it converges with, you know, linear time at around 2026. Hopefully it's not going to be then. Hopefully it's actually going to be, you know, right now, what the planned date is October of this year. Is that correct, guys? For James Webb?
I think they delayed it again, didn't they?
I think they delayed it again, but.
And they're renaming it.
Are they?
I've seen the ELT, the Extremely Late Telescope.
Oh, I love it.
I've seen there was an article written by colleagues in Scientific American that's proposing to, you know, we should have it renamed because James Webb did some not nice things from, you know, 50 years ago or 60 years ago, and so people are trying to pledge to make them change the name. I don't know if that'll happen or not, but yeah,
there's time for it still.
There's time for it. Yeah, it's not up there yet. All right. The supermassive black hole in the M87 galaxy is named Powehi, meaning embellished dark. Say it again.
Powehi, I think.
Powehi. Oh, okay. Forgive me. Forgive my poor pronunciation. Meaning embellished dark source of unending creation. In what language? I really like that. Maori, Navajo, good options. Hawaiian. Okay, some other agreement with Hawaiian. I really just like embellished dark source of unending creation. I mean, that's like got some oomph.
Yeah,
I
I
wonder
know.
though, is a supermassive black hole really an unending creation or more like an unending destruction? I guess it depends on your perspective here. Hopi, okay. That's a good one. Well, indeed, the answer is Hawaiian. There's one of the cool images that Junhan was showing earlier. So yeah, that's pretty wild. I didn't realize that there have been a few different Hawaiian names for a few different things. Britt, you mentioned earlier that there's like a distant quasar that has a Hawaiian title. Is that right?
Yes. Yeah, there's a lot of really exciting work going on in Hawaii right now, reclaiming astronomy culturally, and a lot of that has been done through renaming. And a recent discovery of, I think, the second most distant quasar, which is 13 billion light years from Earth, has been named Ponio Owaina. I think I apologize to any native Hawaiian speakers, but that too is a similar meaning, which is roughly translated as unseen spinning source of creation surrounded with brilliance, which I just love.
Ooh, surrounded with brilliance. I want to figure out how to say that. Add that to, like, if I ever have a child, add that to my child name. Surrounded by brilliance. Cool. Very cool. I dig it. Okay. Let's see. Next question is, what crater is located at the geographic south pole of the moon, not the Earth, and it's thought to be a good lunar base location? I will also add that it was featured heavily in the television program For All Mankind, which is on Apple TV, that I've been watching over the past couple of months. Pretty good. It's a pretty decent, it's not entirely accurate, but has some pretty good dramatic and scientific elements to it. Clavius, Shackleton, okay. Titan, Ropa-Dopa. I like that option. Nightmare, Maui, Craterville, Crater McCraterton. That's the one that I was hoping for. Love when that makes an appearance. A couple of spellings of Shackleton. Indeed, oh, Amundsen, yeah. So indeed, the answer is in fact Shackleton. Of course, named after, is it Ernest Shackleton, the explorer who first made the trek towards the pole, but he didn't actually reach the pole, right? That's why it's Amundsen Scott base, because Amundsen and Scott were the first two, but Shackleton turned back, I think, right?
That's right. He didn't reach the pole, but his story is just tremendous, and yeah. Mm-hmm.
Yeah, I've been meaning to read that. I find like the age of exploration to be super interesting, especially with respect to some of these extreme locations like North Pole and South Pole. Yeah, so it's at the lunar pole, and what makes it special, of course, is that at the lunar pole, because there's not the same tilt that the Earth has when the Earth rotates. So the pole, in the summer in the northern hemisphere, the pole gets a lot of sunlight, and in the summer, the southern summer, the South Pole gets a lot of sunlight, but the moon doesn't have that same tilt. And so basically the inside the crater at the North and South Pole, at some of these craters like Shackleton, they never see sunlight. So it gets super, super cold. There's no atmosphere to like spread out to diffuse heat from elsewhere on the planet or the planetoid. And so it gets super, super cold in there. And we've found ice. Like there are orbiters going around the moon, and they image down and look for reflected signals in the infrared of different molecule signatures, and there's ice hanging out in the middle of this crater because it's so cold there that any kind of ice that or water that ends up on the surface, when it goes into that cold trap, it just sticks because it's like 10 Kelvin or 20 Kelvin in there. So of course, people want to go build a base there because you can access water ice, and you can use that as a, for humans to drink and humans to electrolyze into oxygen and use that for fuel and for breathing and all sorts of things. Water is an essential element. So yeah, if you have Apple TV, I encourage you to check out For All Mankind. It's pretty good show. Have you guys seen it?
It's been recommended to me though. I have to get Apple TV. That's like the one thing I don't have TV wise.
Yeah, I know. There's too many of these different video services. It's hard to. I kind of split between the various ones. I'll have Netflix for a while, and then I'll be like, maybe I'll try out this Apple one. Fortunately, Apple's pretty cheap. I think it's only $5 a month, which is nice. Apple is not paying me to. I'm just
Yeah, Cameron, can I add something really quick? If you're interested to know what Shackleton did and their adventure, I feel like I'm a bookseller, but I recommend this Endurance. Yep, by Alfred Lansing. Yeah.
Oh, cool.
Can you see it? It just doesn't work. Anyway, so yeah, there's a book called Endurance, and they're not paying me either.
They're not paying it. Yeah, we need to get endorsement checks for all of the hard work we're doing to sell consumerism through our high profile YouTube channel. No, that sounds cool. I'll check that out. Endurance. Okay. In what constellation is the North Star? The North Star. What do people think? And can you find it in the sky? That's the key. Polaris. Okay. Ursa Major, Little Dipper. Lots of options here. Ursa Minor. So, not revealing anything, but the North Star, the reason it's called the North Star is that it basically aligns with the rotational pole, the rotational axis of the Earth. Remember, the Earth is tilted like my beer can, and it's rotating around, and out that rotational axis, there happens to be a star there. It's not anything special about that star. It just happens to be the location where that axis is aligned at this point in time. But the Earth is slowly processing around in its rotation axis. So in like another 1,000 years, it's not going to be pointed at Polaris anymore. It's just at this moment in time, there happens to be a star very near to the location of that. And in the South Pole, there's no South Star because there just doesn't happen to be a star at the exact location of where the rotation axis is in the Southern Hemisphere. So anyway, it looks like people are generally agreeing on Ursa Minor, the little bear, and that is indeed the answer. So if you find the Big Dipper in the sky, which most people can, even professional astronomers who don't know that much about finding constellations in the sky, most of them can find the Big Dipper. And then these are called the pointer stars because they point towards the North Star, also known as Polaris. And then the Little Dipper is kind of hanging off of that. But for the most part, it's hard to see the rest of the Little Dipper unless you're in pretty low brightness skies away from a city. But the Polaris is bright enough that if you follow those stars, this is kind of the only star in that vicinity, and you'll be like, oh, there it is. That's kind of cool. And then you'll be able to, know which direction is north, which is actually kind of useful if it's a clear night. So, but yeah, as I said, it's Ursa Minor, the little bear. I always think this is so ridiculous. You've got these people make these illustrations of what the constellations look like. Does it look like a bear? Those things look like bears. Bears don't have a big tail. What is this? What is this? So yeah.
Imagination.
You'll note that this is an incorrect visualization too, because the pointer stars should point towards Polaris, which is over here. So they like, I don't know what the authors of this illustration were doing.
That is bad.
Yeah, it's pretty bad. It's pretty bad. I mean, first of all, these images don't even really look like bears. But yeah, it's not.
That is, yeah,
Anyway.
problematic.
What was the name of speaking of bears and animals, what was the name of the first animal to orbit around the Earth and return alive? Do you guys know?
I think I know the answer. Yeah.
Laika is an option. No cheating, people. Ooh, lucky. Yeah, they would be lucky. Neil, he was an animal. That's true. Neil was not the first person to orbit around the Earth, though. Laika. Ernie, okay. Ham the chimp, yes, indeed. Yuri. This animal preceded Yuri by a year or so.
Love the answers.
Yeah, this is pretty good. All right, so the consensus is generally that it was Laika. The key in this question is, what was the name of the first animal to orbit around the Earth and return alive? Laika was indeed the first animal to go up on Sputnik 2, but Laika died in space. There was never any plans for Laika to come back. Laika went up and died of heat exhaustion when it got too hot in the capsule. It's very sad. So I do see the correct answer here. A late entry, Bielka. So it's actually two dogs that went up together, Bielka and Strelka. Bielka means squirrel in Russian. It's like a common name for a dog in the same way that Spot is like a common name for a dog in the US. And Strelka means little arrow, I think. So yeah, these two dogs went up and spent like a day orbiting and then came back down and survived.
Did they remember to open the windows this time?
Yeah, it was getting pretty hot, but they allowed them the electric window opener to, yeah.
Very humane.
What's interesting though is if you go to Moscow and you go to the Cosmonaut Museum, you can see taxidermied Bielka and Strelka, which is a little bit morbid. This is them. I do like that they have Strelka looking up in the stars in the taxidermied version that will live indefinitely. But yeah, you can visit Bielka and Strelka in the Cosmonaut.
Did you take this picture?
I did not take this picture. I did take pictures of Bielka and Strelka, but I did not take this particular one.
Mm-hmm. Wow.
Yeah, but yeah, the Soviet Space Agency used dogs to test out, how practical it was to keep something alive in space before they put Yuri Gagarin up a year later. The Americans, like NASA, primarily used, as people alluded to, chimpanzees and more, humanoid mammals as opposed to dogs for their testing. So Ham the chimp was used.
Did Ham live?
I think so. Yeah, I think so. I don't know. Laika is the only animal that I know that they sent up with the express intention of never bringing back down. I think there were animals that didn't survive for like, oh crap, that rocket crashed, but nothing where it was just like, well, see you later, good luck, you're not coming back. But I might, I need to do more research on it to make sure, but that was my understanding anyway. Okay. What astronomical consortium just released a dark matter map of a large portion of the sky? This was big news in the last couple of weeks.
Indeed.
ESA, the European Space Agency. Good guess. Other guesses? The Sith, indeed. We already passed the Star Wars question, but someone true to heart. Darth Vader released a dark map of a large portion of the sky. Star Chamber. Okay. Noir Lab. Okay. NASA, Hubble. Some good options here. Another vote for the European Space Agency. Those crazy guys. Those crazy guys. Jet Propulsion Lab. Outback Steakhouse.
I remember that.
That was great. That was from sorry. That was a reference from last month. It was when the when, we had a trivia question about there was a Chinese mission, a rocket that was sent into near Earth orbit, and they allowed the thrusters to just have like an uncontrolled re-entry back into the atmosphere, which was largely seen as dangerous and a hazard to life on Earth. And the question was, where did it end up? And the answer was Maldives, but someone had put in the Outback Steakhouse in the Maldives, which maybe it was the alcohol, but I found extremely funny. So
That was my favorite.
I appreciate that somebody. I was laughing about that for days. I appreciate that someone remembered that. Hershey's. Anyway, Space Force. The answer is the Dark Energy Survey associated with Noir Lab. So that was partially correct. The Dark Energy Survey is this ground-based mission to essentially map out a large portion of the universe and looking at a few different characteristics, including clusters of galaxies, looking at weak lensing behavior. So any kind of gravitational, any kind of mass will affect the space-time around it and warp the images from background objects from our perspective. And so they did this and essentially pieced together the positions and angles of galaxies in the far distant background and saw how they're warped in particular ways, and were able to construct kind of a map of what the dark matter distribution is in the foreground of the galaxy. They were able to do this for roughly 1/8 of the sky. This is just overlaying that on kind of a whole image of the sky. The ring you see here is the disk of the Milky Way galaxy. You can see the large Magellanic Cloud and the small Magellanic Cloud, which are small galaxies orbiting the Milky Way that you can't see from the northern hemisphere. They're only visible from the southern hemisphere. And then this is kind of the position of that map. And, there were some news sources that were like, oh, it indicates that Einstein was wrong and blah, blah, blah. Not really. This is the results that the dark matter map show a very slight deviation from what is predicted by our current cosmological models, like lambda CDM, consistent with the Planck results of the cosmic microwave background. And, there's like a 2 or 3% deviation, but that's not huge considering how many other factors are at play here. So I think it's a super cool result. And this is just the first data release of the second data release from the Dark Energy Survey. And so we should expect to see more in incoming years as more analysis is done. Junhan, are you associated with DES at all? Have you done any work with DES?
No, not at all.
Okay. Well, because I know you do a lot of cool stuff with clusters and Sunyev Zeldovich and
Yeah, I just started. I need to read those papers though. Yeah.
Yeah, there's like 27 papers.
Yes.
Yeah, it's a lot. It's a lot to go through. But very cool result. Very cool result. And that's the end of our presentation. So hopefully everybody got all the answers right. How the heck do I get out of Zoom? Here, stop share. Okay, great. Yeah, so hopefully people got something out of our pub trivia there. Yeah, you guys want to talk about anything else? I know it's quite late for you, Britt. It's like after midnight now.
Am I looking glassy?
No, you're not. You've been super, on the ball. So I appreciate your alertness despite the late hour.
No, this is fun. Yeah. Usually I'm just watching Netflix right now. So this is much more productive.
Cool. Well, let me just check in on the audience, see what's going on over here. Okay. Looks like we're okay. So, yeah. So anyway, thanks to both of you guys for participating tonight. Thank you for your excellent presentations and answering the audience questions and sticking around through the pub trivia. Audience members, thank you for your participation on a Monday evening. Much appreciated. And keep in mind, so we have an all Chinese Mandarin event in a week. So if you happen to speak Mandarin Chinese, that will be next Monday night at the same time, and will be broadcast on YouTube Live as well as Weibo. But you can check our site for that. Our next English language Astronomy on Tap won't be for another month. I think I'm settling on it being middle of July 19th, but it will be our 5th anniversary of Astronomy on Tap Los Angeles. So it's going to be a splash. I might even have a giveaway with prizes. We're going to try and make some like pre-recorded YouTube videos explaining different things in science instead of having these long 2-hour long live sessions. So there's going to be some cool stuff. So stay tuned on that. And then we'll have a public lecture in a few weeks' time, I think, on particle physics, but I can't be sure. But again, I will announce that in our YouTube channel and on our Caltech Astronomy Outreach website. So yeah, I think those are the announcements for now. Anyway, thanks everybody. Hopefully I'll see you next week. Hopefully I don't die trying to get lava out of this volcano in Iceland later this week. But if I come back, I'll bring cool chunks of fresh lava. Hopefully they'll have cooled. Anyway, have a wonderful night, everyone. Thank you for your participation. Let's see.